Okay, good morning, everyone. How did the homework go? Can we do 6, 9? Okay, 6 and 9. Any other questions? Okay. And I will ask again, it's not 11 yet, but, and 61 band is 11.10, right? Yeah, okay. And 6 and 9 should be this section. All right, we can look at all those. Any other questions before? Okay. So I look at 6 is 11, so we can start. I look at 61 first, and then I go back to section 11.11 and answer the question. So since I put those online, I have to number them. So number 61. Oh, okay. I didn't do those problems on, but I assigned them to see if you guys do those stuff. X minus over x squared. Okay. And The question is to find the limit as x goes to 0 of this expression. All right. As x goes to 0, let us analyze what we get. The denominator goes to 0, and the numerator. As x goes to 0, this one goes to 0. 1 plus x goes to ln of 1. ln of 1 is 0, so this is type 0 over 0. Okay, so one way to do this problem is using L'Hopital's rule. Of course, we can do it this way. But here, they don't want us to use L'Hopital's rule. Here, they really want us to slowly internalize the idea that ln of 1 plus x is basically a polynomial of infinite degree. So what they want us to do is to substitute ln of 1 plus x by its power series and compute the limit. So they're really after us to kind of memorize those power series. So what are they talking about? So this is going to be the limit as x goes to 0 of the following: x squared, x minus. So instead of ln of 1 plus x, I'm going to write the power series of ln of 1 plus x. So, of course, you guys will have that in case you have a problem along those lines. So, what is the power series of ln of 1 plus x? I'm basically in front of you looking at the book on table 1. This is equal to x minus x squared over 2 plus x3 over 3 minus ... Okay? So what I'm really physically doing is substituting ln of 1 plus x by that, because mathematically those are equal to each other. So it's going to be equal to the limit as x goes to 0 of, this is x squared. Let's see how we get here. We get x minus x plus x squared over 2 minus x cubed over 3, and so on and so forth. So this is going to be equal to plus x minus x, just simplify, and the limit as x goes to 0 of x squared over 2 minus x cubed over 3, the whole thing over x squared. So this is equal to what? Now I will divide term by term. So it's x squared over 2 divided by x squared minus x cubed over 3 divided by x squared. So if I do that, what I will get? X squared over 2 divided by x squared is going to give me a half. Am I right? Minus what? x3 over 3 divided by x squared will give me what? Quick, help me out. I want to make sure that you follow me. Give me x over 3. And here I should have a term. Now, which term I should have here? Just to make sure this, if this x cubed over 3, this will have to be x4 over 4. So this is x4 over 4 plus so on. So if I keep going here, this will be x4 over that, x squared over 4 plus etc. So when x goes to 0, that's going to go to 0. That goes to 0. You're going to have x to the power 3. It goes to 0. And the limit is going to be equal 1/2. Okay, so if you had used L'Hopital's rule, you will definitely going to get a half. Absolutely so. So even L'Hopital's will give you a half, but here they really want you to use the idea that we can substitute the function by this polynomial. And instead of dealing with the ln of 1 plus x, we deal exactly with its power series. And the limit is going to be equal to 1/2. Okay, that's the idea. When I was taking this course during the Stone Ages, as far as you guys are concerned, they forced us actually to find a lot of the limit using power series. And the idea is they wanted basically to build our ability to memorize those and to use them with some kind of flexibility. All right. So that's for 61. Now they have a lot of other problems, and I'm going to assign more of those for tomorrow, so you guys start practicing using power series in solving questions. Okay, is that clear? Everyone? Great. So now let us move on to problem number 6 and problem number 9 on section 11.11. 6 and 9. 6 and 9. There we go. Okay. Before I go to 6 and 9, which is of course I'm going to already talk about them, I've asked you yesterday on the homework to read the last page on my notes, because I definitely wanted to make sure all of you've read it and understood it. So in my example number 2, I took the function f of x equal ex. And my question was, find the Taylor polynomial centered at 0 of f up to degree 4. Now there are two ways of finding Taylor polynomial. We can use the formula that I will have to in some problems. But the Taylor polynomial, I keep reminding you, at a equal to 0 are nothing more than the partial sums of the Maclaurin. So if I know the Maclaurin series of a function, so if I want the Taylor at 0, and I know the Maclaurin series of a lot of functions at 0, to find the Taylor polynomial, actually I don't have to do all the work. I just go by the function itself. So ex, this is its Maclaurin series. If I want to Taylor up to 4, I can pick them up immediately from here. So the first degree Taylor polynomial is 1 plus x, which is basically the tangent line. So what I mean by that, if you sit down and compute f of 0 plus f prime of 0 times x, you get exactly 1 plus x, because that's where this is coming from. The Taylor polynomial of degree 2 is going to be 1 plus x squared over 2, and that's exactly the parabola that we talked about. Of degree 3, you pick up the first 3 terms all the way up to here. Of degree 4, you get the first 4 terms of the power series, because the Taylor polynomial at a equal to 0 are nothing more than the partial sums of the Taylor series. So if it's function like ex, because I know it's Maclaurin at 0, I can pick up all the Taylor polynomial from the Maclaurin. Usually, the minute I give you Taylor polynomial at a number a, which is not 0, at 2 or 3, then you have to use the formula, because we don't know the power series. So in this problem, again, I ask you to graph f and its Taylor polynomial on the same screen, and we were going to see them in a minute, because I want you to internalize it. So I definitely want to share with you, and I think I can do better today, share with you e to the x, and I think, okay, what is it? Taylor polynomial. I hope it works. No. No, I decided not to work today, like yesterday. Any idea? What shall I do? All right, sorry. Okay, I don't know why this is not working today. Okay, I'll go back. So you guys have the website, and the idea is, if I start drawing those polynomials, I'm gonna try, I can, yes, if you can do it, Christian, just do it. It will help me out. Can you do it? And you can share the screen. I could see it fine. Somehow I want to talk about it. I cannot pull this up for some reason. I'm being very stupid, absolutely. Okay, my apology. So this is gonna be my function f. So this is e to the x and e to the x, and that's okay. And okay, this is e to the x. And then we're gonna work with the Taylor polynomial. Always the first one is the tangent line, which approximate very, very little bit around 0. And as I move on, and equal to 2, actually this is 1 equal to 8, and equal to 2, that's give me the parabola we're talking about, a better approximation than the first one. And then n equal to 3. As you can see, the approximation is still getting better, but not great. It's still located around 0. But as I move farther away, as I give more and more term, the approximation get better and better. That's really what's happening. So basically, if you guys see, if I am like at -1, whether I plug -1 in this polynomial or I plug -1 in the function itself, we should get almost the same value. And I will keep going. As we are now, of course, this is really pushing it. But the idea is that if I keep taking larger and larger n, my polynomial, my function, they almost have the same value. But intuitively, if I don't want a polynomial of degree 14 because the math will be hard, if I want to approximate exponential by a Taylor polynomial, near 0, that's where I get the better approximation because I don't need a lot of terms. So if I need to approximate it, need x equal to 4, I would rather use Taylor polynomial at 4 to get a good approximation of the exponential at the point x equal to 4. So that's really the idea that locally at 0, if I use this as my center, my function and my polynomial are very much the same. That's why I can mentally replace e to the x by its Taylor polynomial at 0 if I am working around 0. And that's really the most important idea here, is the absolute most important idea in this problem. All right, so this is my example here. Okay. So now my last piece was the following. Compare the value obtained by ex and the polynomial at x equals 0.2. And here I just plugged in 0.2 in the expression of the polynomial and 3 in the expression of the polynomial. And I started computing them, comparing them to the actual value. And we realized if I am very close to 0, the fourth degree Taylor polynomial almost gave me the exact value of the exponential. But as I got farther away, at 3, the fourth degree polynomial is farther away from the actual value, just because we're very, very, very actually far from 0. However, and as I would like to point out, as I take larger and larger polynomial, we start getting close. So for the exponential, because the conversions happen for all values of x, even if I take x large, I will get the polynomial coinciding with the value of ex, but I need to compute very large degree polynomials. If I am close to 0, then I don't need a lot of polynomial to approximate the value. Right. So with this in mind, I'll go back to number 6 and 9 because I want to make sure that you guys get this. And I will do number 6 and 9, and then we finalize this piece. So number 6. So number 6, I have the following function. F of x equals e to the minus x sine x. And they want me to find the third degree Taylor polynomial. Okay? And they want me to find it at a equal to 0. Okay, now I have two ways to proceed. One is use the formula. F of 0 plus f prime of 0, x plus f double prime of 0 over 2 factorial, and so on. That's one way to proceed. Another way to proceed is, because it's at a equal to 0, I know how to write this function as a power series, and I know how to write this one. I can just multiply them by each other using the same approach I used yesterday to find the third degree Taylor polynomial. So two ways to do those problems. You decide which one is the easiest. Now, for me, I don't want to mess up with computing derivatives for this function. And because it's a equal to 0, so I am safe. So the way I will do it is what we did yesterday. I take e minus x, find its power series. Now, what's the power series of e minus x? It's the same thing as ex, but I substitute minus x for x. So it's going to become 1 minus x plus x squared over 2 factorial. They want me to get the third degree Taylor polynomial. It means everything after x4, I don't really care about it, plus x3 over 3 factorial plus so on. Sin x is x minus x cubed over 3 factorial plus x5 over 5 factorial, which is I really don't need. Now I'm going to multiply, and I only want the third degree. Means I'm only interested in coefficient of x, x squared, x cubed. I'm not interested in anything else. So I multiply. So I distribute. So I'm going to get x minus x3 over 3 factorial. x5, I don't care about it because I want the degree of order 3. Now I proceed. Minus x squared. And do I need x times x cubed? No, because this is x4, I don't really care about it. I know it's somewhere in here, but I don't care about it. Plus, I'm right here. X cubed over 2 factorial plus minus, it's going to give me x5, bunch of terms. I know that there are a lot of terms here, but I only want T3. No, it's E minus, yeah, so EX is 1 plus x squared over 2 factorial. So if I substitute minus x, yes, okay, that's what I get. So now I just want to combine the term that makes sense. So I will have x minus x squared, because I want the third degree. For x cubed, basically, I have to combine those two terms. So I will factor out my x cubed, and I will be left with 1 minus 1 over 3 factorial plus 1 over 2 factorial, and there are a bunch of terms. And so this is going to give me x minus x squared plus minus 1 over 3 factorial. It means this is will give me minus 1 over 6. So I will have here minus 1 over 6 plus a half, which will give me minus 3 plus 1. So minus 3 plus 1, so it will give me minus 2 over 6 x to the power 3, which is x minus x squared minus a third x cubed. And there are a lot of terms because there are the terms that involve x4, x5. So, and that's not what I want. I only want the third degree. So my third degree Taylor polynomial will be x minus x squared minus a third x cubed. So that's the third degree. So when I am basically close to zero, I will have a good approximation. It means when I am close to 0, e minus x can be almost take the same value as this. As I get away from 0, I need more terms to approximate that. I will be able to approximate it, but I need more terms than the third degree Taylor polynomial. So the way we use those ideas is depending how close we are to 0, the closer we are, the lesser the polynomial with lesser degree we need. The farther away we are, we need polynomial of higher degree. In this case, we move to Taylor polynomial at a different point. Okay? So that's really the idea. Now let us check our work. For the last time, I will try again to share the screen with you and see what we got. This time it's working. So my function now is, I'm going to change my function, is e to the minus x, e to the minus x, and times the cosine. It's going to be a very weird function because the sine is, of course, going to, and so let's do that. And do I expect a weird behavior? Yes, I do, because the sine oscillates. And I want it to, that's sorry, a equal to 0. That's the piece I don't want to change. Okay, and we want n equal to 3, so we're going to get a little bit here. That's 4, and that's 3. And that's exactly the polynomial. As you can see, the green is the actual function. The red is the polynomial. And as you realize, near 0, you can barely distinguish the value of the function from the value of the polynomial. And that's exactly what we got. Because if I simplify 2 and 2, I get x squared. 2 over 3 factorial, that's going to give me 1/3 times x cubed. And that should be what we got. I seem to be having a sign change. You guys fix the sign. All right, and that's really the idea. Okay. All right. So this takes number 6. Any questions about number 6? Finally, we're going to look at number 9, and then we move on. So number 9 is the same idea. Number 9. Okay. So we have the following. The function is f of x equal x times e to the minus 2x. And again, at equal to 0. Okay. Again, I'm going to ask you this question now for this problem. How are you going to find T3? So I write to find T3, we can go 2 ways because it's a equal to 0. One way is compute those. That's one way. Means you have to compute all those derivatives. That's one way to do this problem. Another way is we just use known Maclaurens because it's at equal to 0. Which one do you want to go? 1 or 2? 2. All right. 1 means you have to compute f of 0. Big deal. F of 0 is 0. No question asked. F prime of 0, I mean, it's not hard. You apply the product rule. F double prime, you're going to apply again the product rule. F the third derivative, I don't know where we get. So we will use this piece because it's easier and it is at 0. So let's do that. First, I want e to the minus 2x. Once I do that, I have to multiply by x. So let me make sure we get e minus 2x. So we start with ex. Plus etc. And e to the minus 2x means I have to substitute minus 2x for x. This will give me 1 minus 2x plus minus 2x squared over 2 factorial plus minus 2x over 3 factorial. So the minus 2x will give me 1 minus 2x. Now, minus 2x squared, it means 4x squared over 2. And I basically don't need this because, no, sorry, I need it because it's T3. So this will give me 8, and that's a minus in here, 8x cubed over 3 factorial plus so. So this will only take care of x minus 2x. Now my function is the product, x e to the minus 2x. Means I have to take x and multiply it by that. Plus 4 over 2 to x squared. 8 over 3 factorial. I don't think I will need it now because I have to multiply by x plus etc. So to get the third degree Taylor polynomial, I only need to take care of all the terms up to x3. So square will give me x. Now I multiply minus 2x squared plus 2x cubed, so I'm distributing, minus 8 over 3 factorial, x to the power 4, and now I am safe. After that, I'm going to get x to the power 5. So the third degree Taylor polynomial will be those. So it tells me if I take a value of x near 0 for this particular problem, and I plug x in here in the original function, or I plug it in here, those values has to be very, very close to each other. So for example, let us use this. So use T3 to approximate the following. The value of the function, let us pick any value, I don't know, 0.4, for example. Okay, and let's see how good of an approximation we get. So I'm going to take the third degree and evaluate it at 0.4. And what do we get? 0.4 minus 2 times 0.4 squared plus 2 times 0.4 to the power 3. And if I don't get a good approximation, it means I'm not doing a good job here. It means I have a mistake here. So this is where those machines are useful. And that's 0.4 minus 2 times 0.4 squared plus 2 times 0.4 to the power 3. My calculator, I don't know if any of you is doing it. My calculator is giving me 8.464. It seems off though. 2 times 0.4 squared plus 2 times, all right. Now let me compute the value of the function at 0.4. So the function itself, what value does it take? It's 0.4 times e to the power minus 2 times 0.4. Okay, there is something not right. Anybody can figure out the mistake? Unless I did something wrong here. I think I did something wrong here. Okay, exactly. So that's 0.208. Okay, that's what you should get because this number didn't really make sense. And now, yes, exactly. And what's the actual value? The function at 0.04. We should get close. Let's hope we got close. So it's 0.4 times e to the power minus 2 times 0.4. Okay, how much did you guys get for the actual value? 0.179. It's not a great approximation. So if I want a better approximation, what should I do? What will affect? What will give me a better approximation? we have to take a higher polynomial. Exactly. That's what will give us the better approximation. That's the idea of doing this. So this is not great approximation. This we need a higher degree Taylor polynomial. Now there is a theory behind this, which I will not work on it this semester, but I have to mention it for you. Now, when mathematicians are doing, or physicists, or any scientists working with those ideas, and they have the following question: how good is the approximation? It means, how, if I want an approximation, I want to approximate with an error of less than, let's say, 10 to the minus 4. How high should I take the degree? And there is definitely the theory behind it. There is the idea of a remainder. So I will talk a little bit about it just to let you know that, you know, those ideas, of course, there is a theory behind them. So I will talk a little bit about that, which is the following. So when I take a function f and I approximate it by its Taylor polynomial, there is definitely a leftover piece because those are not equal. So there is a leftover piece that we usually call Rn of x. And Rn means the remainder, which is intuitively, so the remainder, which is intuitively the error that we do when we approximate. So whenever we are approximating by Tn, there is a little bit left over. This leftover is called the remainder. And there is a formula that gives me how good is the remainder. So there is something called the remainder formula. And the remainder formula tells me if I take the remainder, so let us say I'm approximating this by like the 3rd degree or the 4th degree. So the remainder is given by the following formula. The denominator is n plus 1 factorial. The numerator is, let us assume I'm doing at a equals 0, just to make the scenario easy, x to the n. And this will be the n plus 1 derivative at a certain point c, where c is between 0 and x. What's this remainder formula actually help people to do? If I know what the remainder is, and I want this error to be less than 10 to the power minus 4, for example, they use this approach to ask themselves, how large can I pick n so that the error is less than what I want? And based on the theorem, they pick the n that will make the problem as accurate as possible. So usually I do this semester, I'm going to skip the idea, but that's really what's going on. There is a formula which allows me to find which value of n should I pick to make the error as small as possible. And that's really the theory behind it. So there is a little piece left, which is called the remainder, because the approximation is not 100%. And we have a formula which tells me how high should I take n to make the error as small as I want. So if I want 10 to the minus 5, of course, I have to take a large n to make it smaller than less than to the minus 5. So there is definitely a kind of a theory behind this to tell me, okay, what the error I want, and I will be able to control the error. So that's really the theory that I decided to basically to stop, not to do this semester. Right? Okay, so before we leave the section, I just want to make sure that every problem I did, I seem to be doing the Maclaurin. So I just want to make one note that, let us say, I don't give you Maclaurin because we have to definitely do without Maclaurin. So I will do just one exercise just for the make sure that all of us are really doing it correctly. So suppose I just want to invent a function on the fly. Suppose I have a function 1 over 1 plus 2x. And the question is find the 3rd degree Taylor polynomial at, let me pick a nice a. I'm going to pick a to be 4. Okay. Now in this scenario, we only have one way to find the third degree, which is apply the formula. I don't have any other choices for this function. So I want to approximate this by a degree, and I want it at a equal to 4. So in this particular scenario, I don't have Maclaurin to work with, and that's in this scenario, I have to go through the whole process. So T3 is going to be the value at 4, so you plus the derivative at 4x minus 4, that's the tangent line, and then the second derivative at 4 over x minus 4 squared plus the third derivative at 4 over 3 factorial x minus 4 to the power 3. Remember, those derivatives are evaluated at 4. So I will do this problem and we proceed. So f of x, so as you realize, I have to compute all the derivative in this scenario because I have no idea what's the power series at a of f of x is. So this will give me f of 4 equal the square root of 1 plus 8, which is a 3. Now, the tediousness of computing derivative and a good review of how to do the computation. Whenever I have a square root, I have no other choice by writing it this way. And the derivative would be a half. Again, I'm not supposed to forget my chain rule, to the power a half minus 1 times the derivative of the inside. So this will give me 1 plus 2x to the minus a half. So the derivative at 4 would be 1 over the square root of 1 plus, I plug in 4 in here, which is 1/3. F double prime, and then we proceed. Again, the chain rule. Minus a half, 1 plus 2x to the minus a half minus 1 times the derivative of the inside. And this is giving me minus 3/2, 1 plus 2x. And this tells me that the second derivative is 1 over, I plug in 4 in here, I will get a 9 to the power 3/2. That's why I picked an easy number. The 9 to the power 3/2, that's give me 3 squared. So this is 1 over 27. So it is tedious, but it's not hard because I did not pick a hard function. So finally, the power to the minus 5/2 times the derivative of the inside. Those two are simplifying. And this gives me that the third derivative at 4 is minus 3 over 9 to the power 5/2, which is minus 3 divided by 3 to the power 5. And this will basically give me the third degree. And then you can check the website I gave you to make sure we're not goofing. So that's the value at 4, 3, plus the derivative, x minus 4. The second derivative over 2 factorial, x minus 4 squared. Then it's the third derivative over 3 factorial, x minus 4 to the power 3. And of course, we're not allowed to do that without some simplification in order. 1 over 27 divided by 2, it means it will become 1 over 27 times 2, which is, of course, we know the answer. And this would be 3 over 3 factorial 3 to the 5 x minus 4 to the power 3. So this is a typical problem. So it means that I'm telling you now that 1 plus 2x could be almost substituted by this polynomial. And the substitution is very good near 4. The farther away we get from 4, it gets worse and worse. And to get a good approximation, for example, of this function here, x equal to 8, I usually use a to be 8. And that's the idea. Okay, so that's a situation where without the Taylor polynomial, without the formula itself, there is no way I know how to approximate this function by a polynomial. If it's at a equal to 0, usually if we know the Maclaurin, we can act, it will become a much simpler problem. Right? Any questions before I move on to the last part of the course and basically the easiest part of the course? Any questions? Okay. All right. So today we're gonna go back, and as I promised you, so this will take care of the series. So we started by the starting series in the following way. We first learned basically series of numbers. And what does it mean to add infinitely many numbers, which is nothing more than adding and adding and adding till we realize we're reaching a fixed number. So basically we compute the partial sums, and if you get to a fixed number, my series converge, and the value we get to it is the sum, otherwise the series diverge. So first we talked about series of numbers. From there, we talked about series that involve a variable x, or x minus a, and we call those power series. Power series, as I said, were general idea of polynomials, and they are used for two things. Some functions are sometimes given as power series. It means you will encounter functions that they don't have a formula. Their only formula is a power series. So that's the story. Usually we have f of x equal x squared. So power series, sometimes functions are given by power series. I know it's very bizarre for you, but you will encounter that. So the output is a series. And the second thing is that almost all functions we know can be written as a polynomial. So we studied power series because all functions can be written as power series, most of them. And second, there are functions where the output is a power series. Now, writing a function as a power series will have two purposes. So if I write ex as a power series, I can approximate it by a polynomial. That's really the most important idea. Second, writing function as power series will help me to integrate function that I don't know how to integrate otherwise. So if I take the function e to the x squared, I tell you to evaluate the integral. There is no way you can do that as a simple function. And the only way to integrate e to the x squared is to actually look at its series and integrate it. There is no way out. No way out. 6 over 3 factorial, and so on and so forth. And then you integrate term by term. So a lot of functions, one of the two important applications is approximating them by polynomial. Because I can approximate them by polynomial, I can integrate almost any function I want, as long as I can express it as a power series. And as your book mentioned, that's the way Newton actually computed integral. He actually computed almost of the integral by approximating them by power series and computing the power series. Okay. So at this note, we finish series and we move to back to chapter 10. I leave chapter 10 usually to the end of the course because I think that's the easiest part. It's actually a lot of pre-calculus ideas with some calculus thrown in the picture. So today, because I have the last 5 minutes, the first section we're going to study is section 10.5. And 10.5 is about conic sections. So what are the conic sections? Conic sections are the circles, the ellipses, the the hyperbolas. And why they are called conic sections. And the book has a nice picture that explains why we have conic sections. So now I'm back to section 10.5 in the book, and the idea of conic sections. So before we go any further, let's see where the word conic section comes from. Okay. Suppose I take a cone, and infinite cone, it's just extent. And I take a plane and I cut the cone, let us say I cut it this way. So I'm gonna add a picture here. So I'm gonna add one picture right here. And I cut the cone basically horizontally. What's the intersection of the cone with the plane? What shape will it give me? Back to you. Imagine a cone, and I cut it horizontally. What kind? We get a circle. Honest to goodness, circle. Now if I take the cone, the same cone, but I tilt the plane a little bit, like the book is showing you, what I get is an ellipse. This oval shape. It's like a circle, but take the circle, move it a little bit like this, stretch it a little bit in horizontally. This is gonna give me an ellipse. So if I take the cone, cut it by a tilted plane, I get an ellipse. Now, again, if I take a cone and I cut it with a plane that does not touch the upper side, so again, another tilted plane, I would get a parabola. And the last piece is the interesting one also. If I take a vertical plane and I cut my cone, I will get almost like a parabola here and a parabola here. But what we are gonna get is something we're gonna call a hyperbola. So conic sections, that's where the word cone is coming from. Those are the cross section of a plane with a cone. This way we get a circle, ellipse, parabola, and hyperbola. What we're gonna do in this section is basically review what's the equation of a circle, what's the equation of an ellipse. Parabola, you know it, I will not really dwell over it, and what is the equation of the hyperbola. And we're gonna go over all of it. So in the last 2 minutes I will only talk about the circle because that's the easiest one, and there is nothing into it, and you should know it backward forward. All the equations we're gonna learn in this section are gonna be easy, but you have to have total mastery of them. So that's why I'm gonna start with the easiest possible scenario. First, a circle. What is a circle? When I say a circle, mathematically what it is. A circle is characterized by the center and the radius. If I give you a center and I give you a radius, we have a circle. Suppose I have the center, CXK. So that's, I fix a center, which is HK. What is a circle mathematically? It means all the points which are at an equal distance from the center. So if I call R, I fix a number R. So the circle is all the points which are at an equal distance from the center. That's what a circle is, and I know that you guys know that. Okay, that's what characterizes a circle. So what is the equation of a circle? What does it mean, the equation of the circle? It means if I take any point P on the circle, what does it mean, the equation? What's the relationship? What's the equation that relate the X and the Y? So finding the equation means finding the relation, an equation that relate the X and Y components. For a circle, finding the equation that relates them is actually basically easy. So, and to find it, we say, okay, what characterizes a point on the circle? What's the difference between point on the circle, so I will draw my circle again, and point outside the circle, because I want to characterize those points. This is it. This is my R, and this is my center, HK. If a point is here, what characterizes it is that the distance from here to here is R. If a point is outside the circle, the distance from here to that point is not R. So what characterizes a point on the circle is that this distance is equal to R. So that's what we're going to use to find the equation between X and Y. So what's going to be the relation? So I know that the distance from P to the center is fixed. That's what characterizes the point on the circle. I will use this characterization to find the equation. So what's the distance from P to the point C? Now, what's the distance between any 2 points at this stage? If you have 2 points, what's the distance between them? Pythagorean theorem will tell me the following. From here to here, so this is x, and this is h. This is x minus h, and this is y minus k. And Pythagorean theorem will tell me that. So this is from P to C is the square root of x. So that's the circle, the most easy, x minus h squared plus 1 minus k squared equal to r. Purely Pythagorean theorem. It means, actually, this is the Pythagorean theorem, the way you know it, equal r squared. And this is the equation of a circle. We use the characterization, the meaning of a circle to figure out the equation. So this is the equation of a circle where the center is h and k. So that's the simple possible scenario. So the equation of a circle centered at hk with radius r is x minus h squared plus y minus k squared equal r squared. In particular, if the circle is centered at the origin, it means h and k, that will be the equation of the circle. Absolute memory of those. So now 2 very straightforward examples. What's the equation of the circle centered at minus 1, 2 and radius a, 4, for example? Now this is my h and this is my k in this case. So it's going to be x minus h. It means minus 1, x plus 1 square plus y minus k, my k is 2, equal to the radius square, which is 4 square, equation of my circle. Now find the center and the radius of the given circle. So what's the center? So h here is 2, k is minus 4. So the center is 2 minus 4. And always remember that the 2 is not the radius. The 2 is the radius square. So the radius is the square root of 2. So that's the easiest conic section we encounter is the circle, and that is equation. Tomorrow we're going to start ellipse. Geometrically, what is an ellipse? We know the shape. When I tell you ellipse, all of us know I'm talking about something like that. So that's the shape. But geometrically, what does it mean? And how we find the relationship between if you take a point on the ellipse, what's the equation that relate the x and the y, and how to find it? Okay. All right. Any question before I let you go? Will this be on the quiz tomorrow? No. I mean, you should tell me yes, because that's what it is. But it will not be on the quiz tomorrow. On the quiz tomorrow, it will be definitely Maclaurin series, Taylor series, Taylor polynomial, Maclaurin polynomial, and how you approximate those ideas. Okay, I will write this clearly. So a lot of Taylor polynomial for tomorrow, a lot of Maclaurin polynomial for tomorrow. All right, any other questions? Okay, I like to remind you that I have office hours at 12. Please, if you have questions, do show up, because I'm there for you. At some point I quit because nobody will show up, but please, if you have questions, meet me in my office hours. Okay? All right, bye-bye for now.